Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today's simple problem around the idea of a piston cylinder and the idea of a polytropic process. Introductory problem, no big deal, no traps. Problem statement reads, a piston cylinder arrangement shown below contains carbon dioxide at 300 kilopascals and 200 degrees Celsius, at which point the volume is 0.2 meters cubed. Weights are then removed at such a rate that the gas expands according to the relation PV to the 1.2 is constant until the final temperature is 100 degrees Celsius. Determine the work done during this process. So we have two states as per usual. On the first state, we have, on both of them, we have CO2 inside. On the first state, we have everything completely defined, right? So 300 kilopascal pressure, temperature, and the volume. So this is, beautiful. Everything that we can possibly need. And then on the second state, we only know the the temperature. Now we've talked about what this means, right? Whenever we have, pressure times volume to an exponent being a constant, this is a polytropic process, right? Polytropic process. And we've done a video just before, right? Our last video was actually doing, deriving a couple of equations that were valid for the polytropic processes. So we can go ahead and apply that idea here in this problem to be able to solve this. All right. So if you haven't checked that out, you can go check out the derivation that we do there. But if not, you don't need to. You can just follow this video along well without any problems. Okay, CO2, ideal gas. What else? Weight is removed. Okay, so on this second state here, we don't have this weight anymore. So this guy is eliminated. This weight is putting it down. What is going to happen here? What's going to happen? Well, if I have the weight in there, I have the weight of this guy pushing down, which means that this CO2 has a certain pressure being applied to it, okay? Once I remove this guy, what's going to happen is that I'm going to be removing some of that pressure, so now I'm going to have, let's say half of the pressure, which means that this guy now, the pressure inside is going to be greater than the pressure on the outside, which means this guy can now expand. This being a piston cylinder device, yes, means that this gas will expand. As it expands, it's using up its energy, so therefore we expect its temperature to drop, and indeed it does, from 200 Celsius down to 100 Celsius. Okay, so on this state 1, what do we know? We know that state 1, our temperature T1 is 200 degrees Celsius, or 473 Kelvin. We know our pressure 1 on the first state is 300 kilopascals. So actually, when I did this, I can actually tell you that this is 300 kilopascals, the sum of the pressures acting on the CO2. And I know the volume one is 0.2 meters cubed. Okay. What about T2? T2, I happen to know that's 100 degrees Celsius, or 373 Kelvin. And then P2, I don't know. What I do know is that P2 is going to be smaller, right? So I do know that P2 is smaller than P1, because I've just removed that block there. So that's going to allow my gas to expand, and therefore pressure 2 is going to be smaller. In V2, I don't know either, but I do know that V2 is going to be greater than V1 because as it's expanding, if it's expanding, the volume is increasing. Beautiful. The last thing that I know is that there is from here to here, we are going through a polytropic process, right? Because it says so, and that the exponent is 1.2 according to the problem statement. Okay, so if I want to know the work, if I wanted to know work as I went from 1 to 2 for a polytropic process, that will be my P, as we just seen, P1 V1 minus P2 V2 divided by N minus 1. Okay, and again, you can check the previous video if you're confused by this. Okay, obviously this is the same. Some people prefer it this way. This is the same as P2 V2 minus P1 V1 divided by 1 minus N. Okay, obviously the same thing. Some people prefer it in this form. It's up to you, whatever rocks your boat. Okay, note that we know, what do we know out of here? We know volume 1 and we know N pretty much. So we're missing a lot of things. So what I'm going to do is I'm going to go ahead and use the ideal gas properties or relationship. It tells me that this is true. And where I have P times V, I'm going to substitute by nRT or MRT. Okay, so this is going to become mass constant T2 minus mass constant T1. This is better now, right? Because I do know T2, I do know T1, I do know this is an ideal, it's a constant, so I know it. I don't know the mass per se, don't know the mass. Okay, but I do know R, and if I know R, that's already, I can use R with the mass value for R, which is already useful. And I also know this guy here. So it's much better, much better this way, right? Less unknowns. And as a matter of fact, if I am missing this term here, what I can do is use, again, this relationship here, because then if I want to know MR, all I need to do is PV divided by T, right? And for state 1, because this always has to be the same, there's no mass leaving the system or entering the system, it means that P1, V1, T1 has to be the same as P2, V2, T2. They're the same. Okay? If they are the same, this means that this guy here becomes MR that multiplies T2 minus T1. And how convenient is that? Because then this means that this is, all I need to do is find out what this value is and everything else I have. And actually, if I look at this, if I highlight this part, I know all these guys, right? Because check it out, M times R, this is P1, pressure 1 is, what was it again, 300? 300 kilopascals, 300 kilopascals. Volume 1 I happen to know, that's 0.2, right? 0.2 meters cubed. And temperature 1 I happen to know, pascals. And temperature 1 I happen to know, that's 200, right? Or 73 Kelvin. Okay, so why is that useful? Because now I don't have the only unknown that I used to have. Pascal times meters cubed, that's joule. This is kilojoules per kilograms. Kilojoules per kilograms. This turns out to be about 1.27 kilojoules per kilograms. Right? Beautiful. Now I'm going to substitute that in there. Everything else I should have. So this is looking out nicely. So this is going to be 0.127 times T2. T2 is 100, so 273. T1 is 200, so 473. And these are both in Celsius. And down here I have 1.2, so this is 1 minus 1.2. Okay, what's going to happen here? This is going to be a negative number. This is going to be a negative number, so my end result is going to be a positive number. What about units? We just saw that this 0.127 is kilojoules per Kelvin. We're multiplying that by Kelvin, and there's no units on the exponent. That's a dimensionless number, so this is just kilojoules, which is great because we're looking for work. And therefore, this turns out to be 63.4 kilojoules. And that's great because that's the answer I'm looking for, the amount of work, amount of energy that is required as it goes from 1 to 2. As it expands, it's using up energy. We can see that by the decrease in temperature, and it's using 63.4 kilojoules. Right? I hope this helped you out. Hope this was useful and intuitive. If it was, consider liking this video. If you have any questions at all, just leave them down below in the comment section, and we'll talk soon.